Happy birthday, Leonhard Euler. Who's Leonhard Euler? Who's Leonhard Euler? Who's Leonhard Euler?
I think every one of you knows what this video is about. Even my daughter knows because she said happy birthday Leonhard Euler, and after that in a second phrase she said on German, where is Leonhard Euler, because she knows there is a picture coming of Leonhard Euler and she just wanted to see it, so she asked where is Leonhard Euler. So first of all, hello and welcome you everyone to this very special video about Leonhard Euler, my personal favorite mathematician of all times. Please don't write me any hate mails because he's not your favorite mathematician, because I think we all can still stay friends with having different favorite mathematicians, don't you think? I don't want to make this video too lecture-like, so I'm just going through some small bits about Euler. Okay, now let's have a look at the picture my daughter was talking about. I think all of you have seen this picture, and if not, then shame on you, but never mind, you can see the picture here. Okay? What is important about this picture is the feeling that I always get when looking at this picture, that while this picture was created, I think Euler was thinking, wow, I'm such a awesome person. And actually this is normal for someone like him. He really was an awesome guy at that time. He was very famous at that time when this picture was done, so it's quite normal. So he's somehow looking very proud when this picture is done. Maybe he was laughing at a joke that the artist did, but never mind. So let's have a look. Where is Euler born? Euler is born in Basel, Switzerland. And he actually did not live a lot in Basel. He almost lived all of his life in Russia, St. Petersburg, and in Germany, Berlin. Okay, this is where he almost all of his life lived. A very important thing, or better, person in Euler's life was Johann Bernoulli, his mentor. These guys were like Obi-Wan Kenobi and Darth Vader. With the only difference that Euler didn't fight for the dark side. And the interesting thing about this was that Johann Bernoulli was the first to really see that Euler had superior skills in mathematics and reasoning and so forth. Actually, Paul Euler, the father of Euler, wanted Euler to study theology. And it was Johann Bernoulli to really convince him to let Euler study maths. The next important step in Euler's life was a competition in which he took part. It was about the placement of masts on a ship, and actually he only got the second prize, not because his idea was not that good. The reason was because he was just too young. I think he was about 16 years old at that time. Okay, and this is just fascinating for a 16-year-old guy to just go ahead and take part in such a competition and do such complex problems. I think if you would go ahead to someone who's 16 years old today, he would just say, what? Okay, so let's have a look at the next important step in Euler's life. This is not a very important step in Euler's life. This is just the important steps in Euler's life from my personal view, because these were the things when I first heard about Euler and was very interested in Euler. Actually, it was about the Fermat numbers, if you ever heard about them. These numbers are looking like 2 to the 2 to the n, and then you add 1. And Fermat really conjectured at that time that all these numbers were prime, and until f of 4 this was true, but all the other numbers became so large that no one had really fun in going ahead and finding a prime number in this. And actually Euler did. Euler looked at this number and he tried to disprove this and found out that f of 5 was divisible by 641. This was a very interesting thing, and I think this is a very important idea about Euler. He was the guy to look at problems and try to disprove them. He really worked a lot on Fermat stuff, and actually almost everything that you hear about Fermat was really proven by Euler. Only a few things were really done by Fermat himself. They are all actually results of Euler. Now, the second important step, in my view, in my personal view, so don't kill me if you are not, if you don't agree with that, it was this year, 1735, when introducing graph theory. Graph theory is a very complex field in topology, and which was introduced by Euler when looking at a very simple problem, the seven bridges problem of Knigsberg. In Knigsberg there are, I think, 7 bridges, like the problem tells you, and the question was if there is any way with crossing every bridge without crossing any bridge twice, and this was solved by Euler. Now, actually, this problem was not only for these 7 bridges, but in general for such paths. If there is a path called Euler path, to go over it without crossing one path a second time. Okay, now this was a very important step in graph theory, and actually if you study informatics, you already heard maybe about graph theory, which were done by Euler. Now, the second thing that I found very interesting was also about the same time was the solution of the Basel problem. What is the Basel problem? The Basel problem was a very old problem, not very old, I think it was about 100 years, and no one could solve this problem. It was this very infinite sum, adding up all the square numbers, and actually not the square numbers, but their reciprocals. And Euler found out that this sum had a value of pi squared over 6. Now I will tell you the story behind this proof. Actually, Euler really evaluated a new method in speeding up the convergence of that such series, and actually the series is convergent but very, very slowly. Now what Euler did was, then after calculating I don't know how many terms in this series, he had a number 1.64493, and looking at this number, Euler conjectured that the series had a value of pi squared over 6. Okay, if the series had a value of pi over 6, and he would have seen this some kind of numerical relationship, but pi squared, really, whoever heard about pi squared anyway? Okay, but that tells you how good Euler's also numerical abilities were. Okay, he was very good at looking at problems and solving them numerically. Now let's have a look at Euler's Opera Omnia. This is, so to say, his main work, and I'm just going over a few of them. We don't have time, and I think I don't have the time in my whole life to go over everything that Euler did, because he did so many things and so many important things that I can only give you a small snapshot of his work. So first of all, he introduced a lot of symbolics, like the sigma sign for summations, the Euler number E, the pi notation. Actually, before him, many mathematicians used the pi notation, but Euler really pushed it into mathematics and making it a convention to use it. He also introduced the I notation for the imagery unit. He also looked at the theory of functions and introduced the f of x sign. Then he went further and introduced, or better, proved a lot of stuff in number theory. The Fermat's little theorem, Fermat's last theorem, he proved for n equals 3 and n equals 4 that there were no solutions. Then he also introduced the Euler's Tottians function phi. He then went and introduced a lot of formulas for partitions. He also was the one who found a closed formula for Fibonacci numbers. He then went ahead and studied sums of powers, aka Faulhaber's formula, if you ever heard about it. Then he also found a alternative proof to Euclid's proof for the infinitude of primes, and he also was the first to prove that the sum of the reciprocal primes was divergent. And he also used continued fractions and Pell's equations and really studied them a lot. Very importantly, these kind of continued fractions are very interesting for theoretical physics. So if you ever wanted to go in depth with theoretical physics, continued fractions is the way to go. Now, another important thing was calculus. He was the first to introduce a numerical method in solving differential equations. He emphasized the importance of power series and really encouraged mathematicians to work on power series, to explore their features and so forth. He also worked on infinite products. He liked this topic. He went also to discuss divergent series, which are very important in theoretical physics like string theory and so forth. And another very important contribution of Euler were special functions like the gamma function, the zeta function, the beta, and the eta function. I have videos on all of them, the gamma, zeta, and beta function. Actually, the eta function is strongly related to the zeta function. So these are his contributions in calculus. His contribution in complex calculus were Euler's formula, maybe the most famous formula of mathematics, and this formula was also chosen as the most beautiful formula in all sciences. He also was the first to use complex calculus for real results like in number theory, and which is very important is he actually laid the groundworks for Cauchy's residue theorem. So he really used complex analysis to find very hard to crack integrals, and if you're interested in the groundworks of him, have a look at my videos about the gamma functions and the Euler integral. And then he worked on the Riemann equations, or actually Cauchy-Riemann equations. He actually was the first to state them, but he didn't see the importance of them in complex calculus. Then, when talking about Euler, you cannot leave out physics. He was also very productive in physics and mechanics and so forth. I'm just quoting three important things that he did. First of all, F equals ma. You might think that it was Newton to first use this notation, but it was Euler. Euler was the first to introduce F equals ma, which is nowadays the standard formula in physics, in school, and so forth. Now, the second thing that he did was the Euler-Lagrange equations, as you can see, which were actually not done by Euler. Euler used these kind of methods for functions in mathematics, and Lagrange used them in physics. And there was also the Euler equations of fluid motion, which were generalized later on to the Navier-Stokes equations. Now, an interesting point here to note, the zeta function is related to the millennium problem called the Riemann Hypothesis, as well as the Navier-Stokes equations. Both of these things are related to Euler, and they are both millennium problems. And if you don't know what a millennium problem is, just Google it. These are actually, I think, 7 problems, and they are the most important problems in sciences, and mathematics almost, and theoretical informatics is also there. And if you can solve these kind of problems, you will earn $1 million. So very high paid problems. And now, when talking about Euler, I cannot leave out this formula, e to the I pi plus 1 equals 0. This was chosen as the most beautiful formula in mathematics, and actually I prefer this way of writing it down, and I will explain you why. E to the 2 pi I minus 1 equals 0. First of all, it has e and pi in it, okay? Like the other formula, it has I, the imagery unit. We have 1, the unit of our natural numbers. We have 0, the natural, or better, the neutral element of addition. We have -1, the first negative number, so actually integer number. I'm talking about negative integer numbers. And what is important about this 2 that I have there is two things. First of all, 2 is a prime number, and secondly, it's the only even prime number. Now, why did I introduce also the prime numbers? Because they are somehow the atoms of our modern mathematics. Okay, without prime numbers, you don't have numbers, and you cannot not do anything. So this is, in my opinion, it contains e and pi, which are transcendental numbers, and also it contains the first prime number, it contains the unit of imaginary numbers, it contains the unit of natural numbers, the negative number, and also 0. And that's actually my opinion on it. If you don't like it, so please don't write me hate mails. Okay. Now let's have a look at the second part of this video. You cannot do a tribute to Euler without showing a proof of Euler, and I will do a very simple proof of Euler. It's about the quadratic equation. I know many of you know how to solve the quadratic equation, maybe all of you know it, and the thing why I'm introducing this in this video is because this is Euler's proof, first of all, and this proof is not very well known. Not many people heard about this, so I hope this is something new to you and it shows you how Euler was thinking. So let's have a look at the quadratic equation. X squared plus px plus q equals 0. What Euler used was Vieta's theorem. I think you know that. It actually is about the linear factors of a quadratic equation. When you have a quadratic equation, you can write it as x minus x1 being the first solution of the equation, and multiply this with x minus x2 being the second solution of the equation. Now, if you multiply everything out and compare the coefficients, you see that x1 plus x2 is equal to minus p, and x1 multiplied with x2 is equal to q. Okay, this is nothing else than the theorem of Vieta. Now, what Euler did was a very intelligent step, okay? And if I tell you, you will ask yourself, why didn't I think of this before? Okay, what Euler did was use a very simple property of numbers. He said that if I have two arbitrary numbers, and actually you can go ahead and generalize this to complex numbers, if I have two numbers, then I can always find a number that is exactly in the middle of both of these numbers. And he called this number epsilon. The difference from epsilon to the other numbers was called delta. Okay, just delta. Now, he just replaced x1 by epsilon minus delta and x2 by epsilon plus delta. Very simply, just look at the picture and you know that these equations are true. And then he plugged it back into the equations of Vieta. For x1 plus x2 equals minus p, he plugged this in and he got this equation. And then for the second equation, where you have to multiply x1 and x2 to get q, he multiplied this. Okay, now let's have a look what happens to these guys. First of all, you see that in the first equation we get a very simple kind of expression that 2 epsilon is equal to minus p. Actually, we can solve for epsilon with dividing minus p with 2. And actually the second equation becomes very easy also. It is nothing else than epsilon squared minus delta squared being equal to q. Now, if we solve for epsilon, we get minus p over 2, and if we solve for delta, we get plus minus square root of epsilon squared minus q. Okay? Now, let's plug in epsilon, and we get plus minus square root of minus p over 2 to the square minus q, and then simplify this a little bit to get p to the square minus 4q over 2 and a plus minus in front. Now writing down both solutions, Euler was clever. Just substitute them back in. x1, x2 was equal to epsilon plus minus delta. Now this is equal to minus p halves plus minus square root of p squared minus 4q over 2, and that's it. This is how Euler solved this equation. I hope you never saw this video, and not this video, but you never saw this kind of proof. And the reason why I show you this is that Euler thought about a way for solving the polynomial of fifth degree. And he knew all the ways to solve them like we do in general, but he wanted a general method for solving polynomials. And this was his idea, and he went ahead and generalized this for polynomials of third degree and fourth degree and found their solutions, which is quite interesting from such an easy idea that the epsilon was in the middle of two numbers. He found such a generalizing idea, and this is, in my opinion, how Euler always thought of problems. He looked at them, and not like everyone used the same procedure. He thought about different procedures to solve this problem. And while using this different procedure, he hoped to find a more general understanding of the problem. Okay, that's actually my video. And I thank you guys for watching this, and I thank Euler for really giving so much interesting insight into mathematics and sharing this with the worldwide community of mathematicians. I really am very honored to be able to do such a video about Euler. I really am a very big fan of Euler, and I hope you are also. And I hope you enjoyed this video, and thank you for watching my videos. I'm really surprised that so many people really like mathematics and really like to do mathematics in their free time, because it's something very, very beautiful. It's a key idea, key way in understanding our world. Like mathematics is a essential thing for physics. Without mathematics we could not understand physics at all, especially the more complicated stuff like quantum mechanics and so forth. Actually, that's it. Go out into the world and tell everyone that today is Euler's birthday, and enjoy this day with lots of cool mathematics, or do something else that you have fun with. Okay, so see you guys.